just a disclaimer.
Okay.
And then I will post the link on the Meetup page.
Meanwhile, Maria, hi, that's me. Aditya, sorry, I did not see your message before, and also less guessing. Okay, that's sorry, I couldn't see your email before. Yeah, somehow I think people in US did not get the link.
I think that's pretty standard. I've been able to go to some groups or in Europe now, but the link doesn't show up. So thanks for posting that.
Yeah.
You need to adjust your username, Mr. Username.
It's actually my work laptop. I have like 4 laptops lying around now, and I have to kind of see which one is working for the Zoom and all. So I have in each laptop, I have
like
one thing.
It's like the first time after a long time I'm seeing his face on it.
Yeah. It's the internet is quite stable and it's working. So yeah. And Maria, before you might have heard about Peter Wittek, right?
Yes, he was a very good friend of mine.
Okay. So is it true that, so he's confirmed as missing, or?
Oh yeah, he's missing since a year almost. And obviously you can't declare someone dead. It's but I guess all his friends and family are obviously not hoping anymore. Yeah.
Okay.
It's a big tragedy.
Okay. Sorry. Yeah.
Just to be ready, when do we start?
We can slowly start.
It's the German academic quarter, I forgot.
I don't think we need to be as punctual as we sometimes are here.
Maybe you want to wait until 50 people on Zoom?
How many people did RSVP on the Meetup?
Like 100, more than
100. So we have, I think we're complete. Like, I think this is everyone who's going to join.
So your guess is that we have about 35% show up?
No, I think a lot of people can also watch. A lot of people can also watch it on YouTube stream. So,
Yeah.
So
30 people are already watching.
Okay, yeah.
Let's start? Or
we can, sure.
If we do that later and later, people will come even later and later, and this is the end.
Sure. We also have a bit of time because we just started the YouTube stream, and people are joining very clearly. I would like, as kind of a segue to the talk before we start, Maria, could you tell us about your background before we dive into your talk?
Sure. So I studied actually originally political science in Berlin at the FU Berlin. Decided that I always wanted to be a physicist, then started studying physics at the Technical University of Berlin. Then I did that for 4 or 5 years in parallel, which was crazy because it's exactly half an hour between the universities by bicycle. And you just like make the next lecture. And then kind of my path took me to South Africa, where I did a bit of political science, then a bit of physics. Then I did a PhD in quantum computing, quantum machine learning. This field was just emerging in that time, and now I'm doing this for like the last 7 years, and it's now a juicy, nice, big research discipline as part of quantum computing.
So you're an academic.
Totally academic, very theoretical. When I say I do hands-on presentations, it's probably the most theoretical you ever hear.
Okay, cool. Then I guess I will mute everybody, and then you can share your slides,
Cool, let me do
and
that.
I can start the recording, and then we can start. Just
It's working?
yes.
Cool. I
Just
can't see
wait.
the chat, so interrupt me if there are questions. Maybe we can just read them out. Or
Sure.
something.
I will mute all. You will be able to unmute yourself. Oh, I guess you cannot.
Okay, cool.
Oh, yes, you can. Good then. Let me start the recording, and we go.
Cool. Thanks so much. Hi, everyone. Good evening. I don't know who you are, but I assume that you guys are all programming enthusiasts, Python enthusiasts, data scientists, people who have done or have gotten their fingers dirty a little bit in machine learning. And what I want to talk about is the topic of basically my research for the last 7 years, as I just said, which is quantum machine learning. And I know this won't be easy because it's obviously like we have to like put quite a basis on quantum computing, because before you can even understand what's the scope of quantum computers and machine learning and so on and so forth. So I will basically focus on one particular angle, which is very software heavy at the moment. And the basic idea before I even start is actually quite simple. It's the idea of taking a quantum computer and using it as a neural network. You tune, instead of weights, you tune physical parameters in your quantum circuit or in your quantum computation. And you interpret the result of measurements basically as predictions. And then we start asking in the last couple of years, like what function classes does that give rise to? Can we say something about generalization? How can we train these models? And a whole ecosystem has been built around this in terms of software. So this is already the whole message of the talk, if it gets like crazy at some stage. Don't expect anything about Schrödinger's cat or something like that. I know when people see quantum, they're always like a bit shocked if you don't start with all the magic of Heisenberg and metaphysics and stuff. This is very like hands-on. Quantum computers just implement linear algebra. This is something you can also like program in a simulator, and you know, want to know what this does to machine learning. Just as a bit of just to set the stage, basically. So quantum machine learning is a term, you know, you hear it more and more since maybe the last 5 or 6 years. It's used in different sectors, and there's a very nice like graphic you can use to show like what the different types are and what we are actually talking about here. So quantum computing is just basically a different paradigm of computation that uses different physics, so to speak, might push the boundaries of what's possible in terms of computation. However, this is very, very hard to characterize. So if you look into quantum computing research, it's very hard to put your finger actually on something. I mean, like newspaper articles always claim it's interference, it's entanglement, or it's parallelism. But if you ask any quantum computing researcher, they give you a very different answer. What's the resource that actually makes quantum computers maybe interesting? So for all matters and purposes, for us, it's just a different paradigm of computing than classical computing. And machine learning, as you all know, is a way of analyzing very specific data if we don't have really an ansatz or an idea how like a model for this data could like look at. So agnostic data science, so to speak. And now there are different ways you can actually combine quantum computing and machine learning. And there are fields like where you use, so you can distinguish them by the type of data you use and the type of algorithm. Is this classical or quantum? And there's lots of really cool research in all those sectors that you can draw from those. What we're looking at is this one here. You give me just your classical machine learning problem that you always work on. I have a quantum computer. What can I do? That's the question. And in some sense, this is interesting because even if you don't think that quantum computers are these crazy machines that can actually do a lot of things, you can view them more as you know, hardware accelerators almost. So what happens if the whole idea of AI and machine learning becomes or gets a different hardware type? And there are actually 2 different types of hardware that we talk about. One that you see more and more used, like, and you know, like developed in the labs of Google, IBM, Intel, academic labs, are these quantum devices. They are, you must imagine them as little chips that are the first prototype of quantum computers. They're small, they're noisy, they don't work very well often. They're often accessible through the cloud, so they're very cool cloud interfaces, so like actually people can play with them. And then there's always this like dubious big idea of one day we'll have the real quantum computer, and what makes this real is that it's bigger, but especially that it's error corrected. So you actually don't have these errors or noise in the computations in your result, but you will have actually like deterministic result out of that computer. And this divide between the hardware is actually very much reflected also if you're interested in this research of quantum computing. And this reflects back to quantum machine learning. There's this good old quantum computing where people do things like in the last 30 years where this has to been developed as theory. And then there's kind of almost the, the folks that do the near-term stuff. And it's a very different way of how to think about machine learning in both two camps. And I'm talking about the near-term idea. So we've got these little devices, they're noisy. What can we do with those? Software, so since most of you are actually programmers or interested in programming, software is like really central to this. It's central to educate people. It's central to prototype and simulate devices before you even have them. So we can just like write software packages where you can simulate quantum computations. It's also important as an interface, and especially in graphical interfaces to quantum computers. And what I show here is like, you might have seen it before, is IBM's quantum experience. Why this one? So almost every company by now has some kind of interface, a nice graphical playground. But IBM were really the first ones to push this big vision of, you can compose your quantum computation, you can send it via the cloud to like New York and do all sorts of shenanigans. And what I'll be talking about, so I always have code examples, and they are written mostly, if they're not written in PyTorch, in PennyLane. PennyLane is a software library that I'm, part of developing and have been like since a couple of years. And the idea of PennyLane is not so much to be software for quantum computers like the others, but it first and foremost in the last years, it was developed to be there for quantum machine learning. So this is exactly the topic that we have. And I'll get back to how it works like just now. Okay, in terms of agenda, I know I don't have a lot of time, and I know you know about machine learning. I just want to work out one or two things, and maybe in a slightly different way of how you usually get an introduction into like commercial ways of thinking about machine learning or practical ways. And then the most time I want to spend on the quantum computing basics. And I know this talk is not about quantum computing, but I want to do it in a way so that if we even stop after this section here, because I run out of time, you would already know quite a lot about how quantum machine learning could be done and what bells and whistles you have to like consider there. But if I've got time, I would like to also look into like now questions of how we can train these quantum computers, how they connect to neural networks, what they actually do. Okay. You see on the left side here always the mathematical notation, but if you don't like formalisms, then just look on the right side. We've got, as most of you know, like 3 ingredients for machine learning, and this is like following statistical learning theory, thinking about this part that is called supervised learning. So it's just maybe a little part of machine learning, so to speak. So you've got data, in this case, like one-dimensional inputs, one-dimensional outputs. Left, you have a regression problem. Right, you've got a classification problem. And this data is produced by some law. And in some sense, the idea of machine learning is to make an ansatz for this law that produces outputs from inputs. Because I always want to like show a bit of code. So in Torch, you would, for example, now write down data in like this Torch tensor data structure. So for example, you've got inputs and outputs, 3 pairs of data. A second ingredient is a model family, and this is actually already enough to understand what I want to do with quantum machine learning later. So just to be like sure that my notation is clear here, you make an ansatz for this like relationship between x and y. For example, you can say like my model family that I use is a linear model, and I've got usually, not in all machine learning models, as you know, parameters that I can tune. For example, in a linear model, that will be the y-intercept or the inclination of your model. And the model takes x and kind of the parameters and produces y. So this is important. We have a whole model family that we select. So your model could be, in PyTorch, something as simple as, this linear model here doesn't even have a y-intercept. And now the third ingredient is a loss, and the loss just tells you, like, what's the error you make. So between your real data and like the prediction of your model. And now, this loss could be just like comparing. You give it 2 data points, it compares them with mean square error. But now here's the crucial point. So what is machine learning? And I actually like only recently thought about it, that you can actually formalize it in this very nice way done in statistical learning theory. You try to minimize the average loss of a model. So for example, this here is the, you know, the inclination of your line in this two-dimensional space I was showing earlier. You try to find the inclination of the parameter or the model, so to speak, that minimizes this average loss over all data you could see, all data in this class. For example, if you look at images, all images that you could see. Obviously, you can't compute this because you can never like kind of do this averaging process over all data you could see. So what you've got is kind of a small data set, and you've got a different, like, call it loss or cost function or average loss. You would call it empirical risk in statistical learning theory. So, and just to say there's like lots and lots in machine learning that you do. For example, regularization, which includes like early stopping, dropout, all sorts of tricks about cross-validation, all those tricks that are built around machine learning in, for example, scikit-learn or other libraries, basically just have the purpose of like bridging the problem that you have only a loss function that you can minimize that's based on the data samples, so the small set of data samples that you see, that it doesn't really reflect the original loss function. So just like to explain this quickly, if, for example, you've got images and you've got images of cats, but they were all like taken on a sunny day, then your green function, which is kind of the loss function of your data sample that you got given, so this very biased data, might actually say the model is the best, which means the loss is the lowest. The model is the best, you know, here where you actually like learn to see like, oh, a sunny day is a cat picture, and if there's no sunny day, it's not a cat picture. But this is like a typical case of overfitting, and what you're trying to basically do is find, you know, minimize this loss function on the data you have, on your empirical like data samples, but as a proxy to actually minimize a loss function that you don't have access to. Why I'm saying this, so this is not so crucial for the rest of the talk. So why I'm saying this is, if you think scientifically about how quantum computing can help machine learning, lots of people think about, you know, how can it just speed up algorithms, or how can it just, you know, like kind of come in as a little accelerator somewhere. But I'm personally driven by this question of how can quantum resources and quantum computer like increase our generalization capacity? So how can we make sure it finds not those solutions that are overfitting and very bad, but it finds like really nice solutions that generalize well? So this is the overarching question that we're trying to answer in quantum machine learning. And I think we haven't even started to formulate the tools for this yet. So we're really at the beginning. Okay, here's a full code example for PyTorch. Obviously, most of you will know how it works. I just want to like highlight it because I will show you exactly the same example, only with quantum machine learning. So you've got the loss function that I spoke about. You have a function that's the average loss that kind of depends on the loss function for each data point here. And now define an initial variable like phi, for example. You define an optimizer, and then you stepwise adapt the optimizer. And what's important here is like this whole do with the backward and what's happening in those steps, as most of you know, is gradient-based optimization. So most of machine learning relies on gradient-based optimization. So you have some information on where to go down in your energy landscape or in your loss landscape, basically. So this is important for just now. Okay, cool. Perfect. No, I never like switch on my timer when I was anyways. Quantum computing. So not Schrödinger cats and not you know, crazy magic, but let's look into quantum computing from a very, very pragmatic angle. So if you were to program a simulator, how would you have to do it? And I use this picture notation all the time. You won't see any cats or bras, if you know, except from those ones here that for me just like show that there's a qubit setting, so to speak. So what is this? You have a system consisting of n quantum bits. And these quantum bits you can just imagine as being systems that
We're losing you.
In one of two states. Sorry, thanks for telling me. Usually after 5 seconds, it comes back. But,
yeah, it's getting better.
So they are, yeah, okay, cool. They just, so it's not the reason that I'm in South Africa that my internet is so bad. The entire city has fiber, only our street is excluded so far, which really sucks. Okay, cool. Please tell me again if it gets unstable. Okay, cool. So you've got these n spin systems, so to speak, and these are the ones, the basis of your computation. These are the physical systems you compute on. Now here's the crux, here's the whole point of what I'm trying to make. The mathematical description of the system doesn't work in an n-dimensional space. So you don't have n numbers to describe this thing, but you describe the system by a vector on array of 2 to the n numbers. Just as a bit of a background why, the idea of how do you interpret those numbers is every entry corresponds to one possible observation I could make. So for example, the observation, everything is in state 0, or the observation, one spin is in state 1, the rest is in 0. So every bit string basically has a probability.
I actually do have a question now.
Oh yes, please.
If you don't mind, if we could sort of express this this physical basis of your observations in terms of these machine learning terms, could we identify them as features of some type of object that we're trying to describe in n dimensions?
Yeah, very beautiful. I mean, I think this already contains the grain of the main message I'm trying to make, or I'm just like reinterpreting what you ask in this way. But let me answer this 2 ways. So in some way, what we will afterwards do is we will encode data in these qubits. And if we encode data, like for example, input X in these qubits, what we actually effectively do, we encode it in this vector here. So we encode it into a 2 to the n-dimensional vector. And if you do machine learning, you know immediately this is a feature map. We map something into a high dimensional space. So if this is what you're asking, then you're absolute genius. Took quantum machine learning like 4 or 5 years to figure this out. So you should come on board. Just to finish this quickly. So this vector that describes basically these measurement result probabilities, you have to read it as follows. You have to think of it as a bookkeeping vector that keeps track of some information that we can turn into probabilities or into a distribution. So think of it as a weird distribution, this vector. How you read is that if you take the absolute square of these values here, and they are complex values, y is a long discussion. It's just a very elegant way of formulating quantum theory, basically. If you take the absolute square values, you get the probability of the event to happen, basically. At the beginning of all quantum algorithms, we say like all systems are in 0. What does that mean? The first entry, which is the probability by convention, actually, that everything is in 0 is 1. Every other probability is 0. So you've got this like, by convention, this like, real 1 and the rest is 0. You could also just have I here, by the way. But yeah, so this is the idea. So in short, quantum systems, all quantum systems you can think of, are always described by, okay, let's see, at least like finite dimensional. Discrete ones are described by a vector of complex values. And usually this is exponentially large. So this vector is intractable for anything, if n is larger than 50, you already can't really simulate it on any computer, on any classical computer. Now I promised that I will show you penny lane code. So, and I hope this really like brings the message home a bit. But let me just quickly describe what happens here. So you import the penny lane package. Since this is or the idea how lots of quantum computations are implemented is the following. You define a circuit, and then you define a device, and then you tie the device and the circuit together, and then you run basically this like circuit on the device. So in penny lane, this looks like this. The device you can specify by the string. You have a lot of different devices that you can specify. I'll show you just now. And the number of these subsystems, so small n is, we call it y's here. So here we've got 2 qubits. So you've got a state of, your space, your largest space in which you calculate is 4-dimensional, 2 to the 2. And now here's this like decorator that ties the device to a function, which we call a quantum function. It's a very specific function that has to be written in a very specific way to implement what you want to do on your quantum computer. And at the moment, we don't do anything except from returning probabilities. So this is, you can do this like it's implemented by just computing basically the absolute squared values of your vectors. If you run it on real hardware, you have to sample to get an estimate of probabilities. Just this is a bit more like complicated information. And if you run the circuit, you get basically this probability distribution over the events. But if you look into the circuit and you ask like, what is the state? So what is actually this thing here, which we always do bookkeeping of in simulators, you see exactly these are complex values here for now. But yeah, so this is exactly this vector that I showed here, basically. And now quantum simulators work just by keeping always track of what happens to this vector here internally, and then kind of like computing probabilities and lots of things out of this. Now we just like need a couple of ingredients to build quantum algorithms. A quantum algorithm can always be described by, like in the picture here, we describe it by this block that acts on these like subsystems. It just means I do some physical operation, some manipulation, I shine laser light, I turn some knobs, whatever I do, but it manipulates those n qubits or these n systems here. And in my really large dimensional space, what happens is I have a linear, so-called unitary transformation of this vector. Why is it unitary? Just because I need to make sure that these probabilities still add up to 1. So I can now transform this vector. Up here, I just show like kind of a visualization of this vector here, and it just turns this vector on a sphere, so to speak. So afterwards, I just get like some other vector, Again, code here, I coded up some U. This is a unitary matrix, so it fulfills all the conditions we need. And here my circuit now applies this unitary, so to speak. And you see that my probability distribution changed, and also my internal state, my bookkeeping state that produces the probability distribution changed. So the state here in the simulator is nothing that in real life is really there. It's just our description of the system, basically. And now you can run the quantum computer in 2 modes. You can measure, which just means you draw samples. For example, you ask the computer, what state are these qubits in? So exactly like in coins, you throw them and then you look and you see like what state are which ones are flipped up and which are down. So you get a whole number of samples from this distribution here. And so in Penny Lane, for example, you can just like change the output type from probabilities to sample here, and then you get, don't worry about like why this Pauli Z, this is like a quantum, specific quantum terms of describing your measurement, but you can get samples out of your quantum computer. The state is still kind of the same as before, but now what you get out of the quantum computer are -1s and 1s, which represent 0s and 1s out of traditional reasons. But now what's important, so if you now sample, you could use your quantum computer, if you use it as a machine learning model, as a generative machine learning model. But if you want to do something like a deterministic machine learning model, like something like a neural net, where you get a deterministic result, it's always the same however often you run it, you don't want a sampler. So what you do, and this is very natural for quantum theory, you measure an average. So instead of getting like a 0, sometimes a 1, you actually get a value like, for example, 0.6, which means 60% of the cases your qubit was in this state and 40% in the other state. And I know this looks like a big monster if you don't do maths a lot, but in this really large space of your description, what happens is something called a quadratic form. So you take this like a matrix vector multiplication, you compute a row vector, a complex conjugate row vector of it, and then you sandwich basically a big measurement matrix that describes your measurement in the middle. So it's not so important what these things are, but the only point I want to make here, to describe a quantum computation, you just have to do linear algebra. So this is a bit nonlinear because there's like a quadratic form, but you know what I mean. It's matrix vector multiplication, so to speak. So this is called the expectation value. It's a different type of measurement, so to speak, and you can just change the sample into xval, and you get like, not samples, but you now get like something else, like deterministic outcomes. This is the expectation value of the first qubit. This is of the second qubit. Could be any value. It's just an example. Okay, now, one last ingredient. Quantum circuits are not like a big unitary blob, like a big matrix that apply, but in the lab, in physics, you do something very local. You address 1 qubit or 1 spin, and then maybe 2. So what happens in your mathematical representation, you have not 1 big matrix, but you have actually a lot of matrix multiplications. And if I don't get to this, this is already interesting because a matrix multiplication is kind of a bit like a linear neural network, you can imagine. So you have modular kind of layers almost that you apply. Okay, I have no clue what I did. Oh yeah, I replaced the unitary now by like, and these gates have different names and there are standards, which gates are interesting and stuff like that. So this is just like a decomposed circuit, a totally random one. Okay, now 2 ingredients after which I can already like basically say how these models are now used for machine learning. First is an insight that, if you open your quantum computing textbook, you won't see this so often. But actually these so-called gates, these manipulations of qubits, are actually just physical things. And very often you've got a physical knob that you tune, like a parameter. For example, the strength of an electromagnetic field, or there's something you can tune in your lab. which means that these gates depend on parameters. So that's nice, right? Like in your network, like weights. And we know since many years how to tune those parameters. Again, let me go quickly to the code. So there are gates, very famous are so-called Pauli rotations. They're called Rx, Ry, Rz. So here I showed one of those gates that takes actually a parameter, so in the circuit. And now the result depends on what this like parameter is, obviously. So this parameter actually defines now not a single circuit, which is a single computation, but it defines a family of models immediately. So you're in the space of machine learning immediately. And the last ingredient that's
a question now related to that.
Oh yeah, please.
So Ali asks, can we do machine learning in these quantum simulators then? And what would be the performance
Yes.
or performance difference compared to traditional CPU GPU models that we have?
Great. Ask me again in 5 minutes. I think I should be ready, and then maybe it's a bit clearer.
Okay.
Cool. Thanks.
Okay.
I actually might not go to the end anyways. So the last bit, you're thinking if you interpret this thing as a model, at the moment I haven't spoken about data at all. But obviously quantum circuits and quantum computations have to depend on inputs. Even Shor's algorithm from the 90s, all of those depend on inputs. So implicitly, the first step that you do on a quantum computer is always like what I'll call the encoding step. So you take a data sample and somehow you have to get it into the quantum state. And now here's what we're talking about here, like what Michael said, is that if you interpret this also as one of these matrix vector multiplications, you do it right at the start. But now this matrix depends on X. What happens is that finally your data vector depends on X as well. So what you do, you embed data into very high dimensional spaces. And this is immediately something you should know from support vector machines, from kernel theory, from a lot of ideas in machine learning, maybe not neural networks so much, but like that were very popular in the 90s. Let me just see what I've done here. Oh yeah, okay, so this is just the circuit with like a parameter, and now I've got also a data point here. Don't worry about why I use this as a keyword argument for now. This has more historical reasons, or yeah. But you see that what I did here actually in terms of data encoding, I can do very structured data encodings, but I could also just throw my X into another rotation gate. And then I have another rotation now called an RY rotation for the parameter. So basically I associate physical parameters with data and with trainable parameters in a very similar fashion. And now I can train the whole thing. And people have done that in quantum control all the time, like since hundreds of years, or 100 years at least. So this is now my trainable model. So in Penny Lane, a full example of optimizing a quantum circuit, so to speak. At the moment, for some reason, I didn't put data in here. Looks actually very much like PyTorch, right? Like, you define an optimizer, and then you have a step of the optimizer, and you can actually like train the quantum circuit. So first of all, yes, the software simulators, not the usual ones. So something like Penny Lane that's geared for quantum machine learning can train quantum circuits. Most of the bigger frameworks, if you heard of Qiskit from IBM and stuff, I think they're kind of slowly trying to get it into their like frameworks, but this software has been really built on this idea. And just a very quick idea that it's built around is that you can really quickly change your devices. So, my internet connection is unstable again.
You're back.
Okay, you warn me if you can't
You're
hear
back.
me. Cool. I usually never have problems with, I don't know, it's the first webinar that doesn't work as I want to, but anyways. Okay, cool. So you've got different devices you can use. You can use, for example, IBM's devices, Google's devices, or simulators. So whenever someone has software, we can write a plugin to Penny Lane. And in the end, it's just a matter of changing this one line, and then you will tie the circuit to a different device and run it somewhere differently. So Penny Lane is completely agnostic on where something runs. Okay, now I don't have a lot of time for quantum machine learning. I just want to give you one more ingredient that hopefully answers a bit of the question of can we train those models? Because I was kind of, lying about, or there's one big hurdle basically. So whole idea is we use quantum computations as machine learning models. I think the first time this was explored in these two papers, and there's a very nice overview here, Benedetti et al. These ones are archive references. So if you type them in with archive, you should, ARXIV, you should actually find the paper. Okay, so this is the whole setup. We can train our models. Now here's a problem. If I want to train my model, I told you before that if we go to higher dimensions, we need gradient information. And it's not necessarily given that if I take, the derivative of this function that was calculated by a quantum computer with respect to a parameter, that I actually get another function that a quantum computer can calculate. So in terms of a bigger picture, if, for example, my quantum model, I call it now a quantum node, is part of a bigger computation, and for example, like a big neural network where a layer is done by a quantum computer, and I want to now backpropagate or differentiate through the quantum computation in order to do a gradient-based optimization. My big problem is that I can run the quantum algorithm, but I don't know how to get gradients out of it. And this was a big insight, like a big building block that almost enabled this whole research field that says the following. I can get a gradient out of a quantum device if I just run the circuit twice, but the parameter with respect to which I want to like get the partial derivative, I have to shift it once to the one side and once to the other side. Now that looks a bit like finite difference rule, just wiggle a bit to the left, wiggle a bit to the right, but it's actually a macroscopic shift. So the geometry of quantum physics really has different rules about how to get gradients out of devices. So if this was a bit much, we can just say we can compute gradients on quantum devices so we can make them part of machine learning pipelines. And there's a whole ecosystem now of new optimizers, like quantum natural gradient. What can we do with shots? Like there's a lot of like work on this. There's a bit of concern because there has been a theoretical results that our gradients might vanish. We have a vanishing gradient problem in these quantum. So there's a lot of research that now like you can play the whole games of classical machine learning and quantum machine learning basically. And I just want to show you kind of the full example. And this one here is a bit different because it uses, so PennyLane can interface with PyTorch, TensorFlow, or NumPy. I showed you the NumPy version, which is kind of like, looks almost like you just do native Python programming. But so this one here is the PyTorch version. So it's almost the first example, but as quantum computation. So it's exactly the same. You define a data, you define a device, you define a quantum circuit. Here I used not single gates, but templates, like already higher order compositions of quantum circuits. You have the loss function from before, the average loss, and then I do exactly the same that I did before in the torch example, but now I'm training a quantum computation. Since I don't get to any like of the rest, you can ask me questions about it. I have a bit on quantum neural networks and stuff like that. But so just to summarize, the big idea now for us scientists is to understand what models do these circuits give rise to. So do they like really like look like a neural network? Do they look more like maybe a kernel method and stuff like that? Lots of people want them to look like neural networks. My personal opinion is that you always have to bend over backwards to implement the nonlinearities in quantum physics. So the best and nicest picture to have is that we map data into these big high dimensional spaces, and then we do linear algebra with them. So and this is very much like what a kernel method or support vector machine does under certain circumstances. So there's very, very interesting theory coming out of that. Yes, and now to answer this question, how well are they doing? And here's a big problem, and I put it on like as one of the questions here. One of the big problems is that in a machine learning paper or in machine learning context, what you do, you benchmark a model to see if it's doing well, right? You report the test error and then you see like, is it doing well or not? We can't do that because our simulations are automatically restricted by this like exploding space that we have to do the bookkeeping in. So we can only simulate like something like, maybe if I want to do it quickly, like 15 qubits. If you do really put all your efforts in, maybe 50 qubits, but then immediately it gets impossible. So we can't use simulators, but the real devices also, they're small, they're noisy, they're not working very well. So we basically try to like think about machine learning in a space where we cannot have access to the models that we're trying to like develop. So what's the answer here is probably like a lot of theory building, a lot of like sitting back and maybe waiting a couple of years while we like try to understand like things on paper, first of all. But there are lots of other good questions. And I say like, there are different questions from, I get often this question like, can quantum algorithms learn better? Are they faster? Are they this and that? We really don't know yet. And it's a very, very high level question. It's almost as big as the question, are neural networks, which neural network is the best? Like you almost can't answer this question. I mean, for no free lunch reasons or something, or whatever. But what I want to say is like quantum machine is really at the beginning, and there are a lot of like smaller questions we can ask that are really, really interesting. And it's a bit about like the domains that QML works on is the idea, can we scale things? Do these like vanishing gradient problems? Can we circumvent them? Can we find special quantum optimization strategies? And there are a lot of like things to work on. Basically, it's a whole ecosystem of work to do to make these quantum models, be part of machine learning maybe one day. That's all I have to say. I hope I didn't run over time, and I hope you got a bit of an idea of quantum machine learning. Yeah, and I don't know if we do questions now or maybe after the second talk.
I have a question.
Me too.
Just asking maybe like the very obvious, the very, very, very obvious question. The simulations are obviously exponential based on the size of your data. But if you had the device, then it would work linearly on that actual size. So then in that case, if you implement a machine learning model, then it would be exponentially faster, or it would take the logarithm of the time that a normal model would take. Is that the correct statement?
I think you have to repeat the last part. Sorry. I got it until you got it exactly right? Like, yeah. So you've got the data. Once you have it in your Hilbert space, you can act linearly on it.
Yes. Now the question is, given the hardware device, if I have, imagine that I have a data set and it would work in the order of N3 on the usual algorithms I have. What would be the computational order now on that on that quantum device?
So I think is the question, for example, in support vector machines, we have to now, if we map things into this high dimensional, or we still have like algorithms that are quadratic in the data.
Yes.
Is this, for example, what you're asking? There are papers that can show that quantum computers can always act linear in the data, and you very easily get quadratic speedups from quantum computers.
Okay.
In terms of your Hilbert space, you're logarithmic in the size of the Hilbert space. So if this doesn't spin, so you're totally right. The only problem is that data encoding will always force you to kind of like be at least linear in the data. And lots of the first quantum machine learning proposals were always saying we have exponential speedups. But this is, I mean, between you and me, this is obviously a very, very weird claim, because you even have to like load the data in the first place. And there's a lot of controversial debate, and now they have all been dequantized, and there's a lot of like forth and back. So to cut a long story short, I think in terms of speedups, which is not my personal viewpoint, but this is the most important thing, we can probably get polynomial speedups quite nicely out of quantum computers. I'm not focusing on them. These small devices, they can't even do most of the algorithms that give us those speedups. So yeah, we can just think
that
about
brings
it.
us to the next question, which I have here, which is how many parameters can we train with the devices we have these days?
With the devices or the simulators? That's the question. So in the devices, if you take IBM Quantum Experience, maybe you have a chip that has 20 qubits. Immediately, if you apply something like, depends on the type of gate, but if you apply 20 or 30 gates, your output is very noisy. So it's not a question of parameters, it's a question of gates here. In simulators, depends on how the simulator is programmed. We have simulators that are programmed all in TensorFlow, for example, that are end-to-end differentiable. And there you can train very quickly like 200, 300 parameters. But you see, we're not on the scale of neural networks yet.
Right. Next question I have is, when can we expect QML to be implemented commercially?
Oh gosh, not for a long time. We wish, we sometimes like tell ourselves, but at the moment, there's a lot of stuff happening in industry and also with companies, but they're always like proof of principle studies or investigations to just see what's happening in the space. But you would always be better off having a classical computer for probably the next 5 or 10 years at least.
Okay, then I guess that also answers the next question, which is how long until people are using quantum machine learning in practice?
Yeah,
Not
if people tell you in 5 to 10 years, it's always like 20 or 30 years. Plus we fell off the Gartner hype cycle recently. I don't know, quantum computing is not there anymore, so who knows?
Okay. Next one. one of the arguments that gets made for quantum supremacy algorithms like Shor is that qubits allow more truly independent parallel sampling of the distribution than classical computing. How does that translate to quantum machine learning? If it does, is that
Yes.
better or stronger sampling could be more useful than brute speed up possibilities?
So the notion that quantum computers are parallel devices or much better than classic computers because of that is honestly, it's complete bullshit. Or if you want to be very nice, it's a didactic lie we tell to the media to say something easy about them. Why? If you think about classical probability distributions, classical probabilistic models live in a space that's as big as quantum spaces. You know, if you describe n classical coins, you've got 2 to the n probabilities. So this parallelism is in some sense just the fact that you work in probabilities. However, there is something that's interesting is that you can interfere probabilities. You can do different things with them. So there is something happening, but we do not really, you know, one of the biggest quantum computing gurus in the world once told me I was trying to develop an algorithm where we interfere things to optimize, you know, machine learning model. And he just said, don't even try to engineer the interference. You just can't do it. It's too structured or it's just not clear.
Right. Nice.
I have another question.
Pardon.
In this one figure that you showed with the input of your cats into this box that would somehow consume the cats, like basically your data input, and then you get some output. So my question is, I mean, each of these features, each of these data points, each of these parts of this entire data point that you feed it, isn't it just another function? I mean, it's how do we even compare it to this classical notion of a data point? I mean, what you are showing us isn't a data point. It's a family of functions that you feed to the system. So I don't fully understand how this even compares. It seems more like if you have classical machine learning, you have some type of universal function approximator, and here you have some universal functional approximator. Is that true? Is that correct? Or am I misunderstanding that or something?
No, I think you don't have functions that you act on. Okay, in a very deep sense, yes, but I think not in the first iteration. What happens, for example, if your data is, let's say your data, you can binarize it, and your data input, let's say it's one dimensional, you can binarize it as 1000. Then you can encode it into qubits. That's one strategy out of many, right? So you flip the first qubit and leave the other ones, or the second one, whichever like it is.
Okay.
And in some sense, this is what happens to your physical system. What happens to your description, in this like Hilbert space, in this description in bookkeeping, what happens is that you change basically the probability distribution.
Yeah.
So the best way to, I think, phrase it, I don't know if any one of you, this is a very technical idea, but like this idea of kernel mean embeddings. So you map data to a probability distribution. That's the closest you get to describe what happens. Just that this probability distribution is quantum and not classical. So think of a Gaussian, you know, probability distribution that just like the parameters are associated with your data. So whatever data you feed in, your Gaussian will be different. Your Gaussian distribution. That's the idea.
Okay.
It's a lot to get your head around, but
but
super
eventually you try to not work on functions, but on the parameters that span these function families, right?
Yeah, you train so this is how you feed your data in, and then you do something very similar with your parameters, and you just afterwards train them because you know how to.
Okay, thanks.
It takes quite a bit, I think, to wrap your head around it, but yeah, cool.
Theo, somebody still moderating?
I think Adrian is okay. Adrian, are you here?
Oh, sorry.
Well,
yes, I was mute.
Yeah, exactly. Okay.
I was moderating the session mute.
Perfect.
Cool. So now we're done with the first one. The recording is finished. We are live on YouTube still. And thanks a lot, Maria. That
Yeah.
was awesome. And I really, really enjoyed that. I didn't
Clap,
understand
clap,
most
clap,
of it.
clap, clap.
Yes. To continue, I forgot a few things that we usually say at the beginning. I'll go over them, and then we'll have a little bit of an interview, and then we'll continue with the second talk. To review, for the people who are new to these meetups, this is a PyData meetup, clearly. It's a part of, PyData is the educational branch of NumFOCUS, which is an NGO which focuses on the PyData stack, and it does a lot to support the PyData stack software and to support people who use that software through PyData, for example. We usually have or different chapters. That's what we call these different PyDatas, like PyData Berlin, PyData Amsterdam, PyData Jeddah. These chapters, some of them also have conferences every year or every few years. A lot of them were canceled this year, clearly. And instead, we are going to have a PyData Global event, which you can find information on the global.pydata.org. Is Matti on the call still? Is Matti mute? He's not. Please go there. If you would like to give a talk, the CFP is open. You can submit proposals already. And I think it's gonna be in November. And if I'm not mistaken, the idea is also to have talks in different time zones, and there are going to be people from all around the world. So it will be hopefully a really nice conference. Oh, Matti is there. Would you like to tell us a few words about the global conference? You're mute. Oh, right. I'm very sorry. I need to find Matti. I asked you.
There we go.
Yeah.
I know I'm on mute because you muted me and I can't unmute myself.
Sorry.
Yeah, so PyData Global is happening, as Adrian said, in November. That's going to be a virtual conference. All the details on how that's actually going to be organized and run, you can find on global.pydata.org. The CFP is currently open for another couple of weeks until the 2nd of August, I think. So we are looking for speakers, but we are also going to be looking for people to help us review all the submissions that we'll get. We're hoping to have hundreds and hundreds of submissions. So we want to open the review process to the community at large. I'm currently actually working on putting all of that together. So there's more information on that to follow. The best way to follow up on that is to either follow PyData on Twitter, or if you're a member of any one of the PyData meetup organizations that Adrian already mentioned, you should get a notification through that system as well. I don't have anything more to say about that.
Cool.
You can mute me again.
Oh, no, you can mute yourself. That's fine. Another thing that I wanted to mention is our code of conduct. We follow NumFOCUS's code of conduct. You're supposed to be nice to each other, like obviously not nice stuff. Sexist, racist, homophobic behaviors are not okay. You can always tell the COC team, you can talk to me or Noah. Noah is now on the call if something happens. On top of that, we are also adding a few clauses because of certain incidents that we had. It's not comfortable conversation, but we should have it. This is a professional meetup. That means that most people, especially women, given empirical data, don't come here to have dates or to be hit on. And when you come to these meetups, either online or in person, that shouldn't be the assumption. Everything should be kept completely professional. If you want to add them or interact with them, with each other on any digital platform, that should be kept very, very professional. And it should ideally be with people's explicit consent. You can, for example, if you add people on LinkedIn, sending a message saying that it was nice to get to know you on the meetup, wink, is not a professional message. That doesn't mean that you can't be friendly with each other or you can't find friends. It only means that everything needs to be very consensual. You can ask, is it okay if we connect on a platform like LinkedIn or Zinc or whatever? And more than that, as long as you have people's consent, it's none of anybody's business. And if you encounter any of those instances, if you receive any of those messages and you're not comfortable with them, it is not okay that you receive them. And you can very, very clearly contact us, and we will take the actions as we do with the other instances of the COC violation that we take. With that out of the way, this meetup, we also had the idea of joining some of the chapters. Since they are virtual, we could also use some of the benefits of having a virtual meetup, like having speakers who don't live in Berlin, but also joining some of the chapters together. And we started this one with joining some of the FOC PyData Jeddah in Saudi Arabia. I gave a talk a few weeks ago in their meetup. And in this meetup, we have Yasmin, one of the co-organizers. And I believe we also have quite a few people from that group as our audience. And I guess I can, with that, hand in the mic to Theo, and he will interview Yasmin and Micha.
Yes.
Just so you know, we're still live. I'm not sure if you wanted to broadcast this, but
are you okay, Misha?
No, I'm okay with that. I'm just saying that last time we didn't broadcast it. That's all.
Yes, we did.
Okay. Yasmin, are you okay if we broadcast that on YouTube? Can Yasmin unmute herself, or should we ask Catherine to do that?
Yeah, I need to do that. You're also co-host. I will try to find,
okay.
Yes, ask to unmute. She should be unmuted.
Hey.
Now.
Hi, everyone.
Yes.
Hello.
Hi. So yeah, is that okay that we also live stream that? Okay, great. So hi everyone. So last time, if some of you were there also, we did like 2 short interviews with 2 organizers, and we will do that again this time. So this time I would like to interview Yasmin from PyData Jeddah in Saudi Arabia, and also Misha, an organizer from PyData Berlin. The goal here is just to show who is behind the organization, and maybe give you some motivation of idea if you want to help to organize a meetup, and or that's also the great thing with the online, you are maybe somewhere else and you think that maybe you want to create your own PyData chapter in your own city. So that's the goal of that. And we are also welcoming feedback if you want to, if you think that question you would like to ask, things like that. So I would like to start with Yasmin. So three questions. First, can you tell us a little more what you are working on at the moment? So what are you doing in Jeddah?
Yeah, sure. First, thank you for inviting me to talk. Basically, we arrange online webinars, as we know, due to the COVID-19 situation. We arrange one meetup each month. We did our first kickoff webinar in June, and Adrian, as he said, he was one of the speakers. Our next webinar will be on July 25th, next week. With Juan Sebastian, he will give a talk about web scraping and beautiful soup. Also, we believe that the Twitter account has powerful impact on people. So we are working on our Twitter account to be more informative. We always share tricks and tips about Python, Julia, and other open source tools.
Great. Yeah, thank you very much. That's cool. I think sharing also on social media is quite interesting. Can you tell me how and why did you become involved in the organization? So
Yeah, my team and I have the same passion about data as well as volunteering. That's why we are enjoying being part of PyData. We are enjoying sharing our experience, the knowledge with each other. Also, we learn every day we learn something new from each other, as well as from our speakers. Besides that, we support our society to contribute in open source software. That's why we felt that PyData is the right place for us.
yeah, totally agree. And what would you recommend to someone who wants to get involved? So I think that what you can ask for someone in Jedi could also be for anywhere in any of the chapter.
Yeah, sure. The best thing you can do it for yourself is being a part of a community that you are interested in. This will reflect on your personality, on your way of thinking. You will be more confident, and also it will help you to increase your connection circle. And we all know about the benefit from that. You will get more job opportunities. Also, you will find people that can project, or you can contribute on a new project. Sorry, my voice is cutting because my internet is unstable.
Can you repeat
Sorry.
the two last
What
sentences,
I'm not
please?
thinking is that pardon?
Can you repeat the two last sentences, please?
Yeah, sure. I was saying that this will help you to find the people that can help you on your current project, or you can contribute with others on a new project. So if you have a chance, don't miss this opportunity and try and be a part of a community, like PyData, for example.
Yeah, I think that's very important. Could be PyData, it could be something else, but be part of the community is helping, I think, to
Exactly.
develop
Yeah. You will
professionally and
find
also
people they
personally.
have the same. Sorry.
Yes, go for it.
I just want to say that you will find the people they have the same interest as you. So yeah.
Okay, so thank you very much, Yasmin. It was really cool to talk with you.
My pleasure. Thank
Yeah,
you
and
for you
you
and
have a
Adrian
meetup
for the
next.
opportunity.
Yeah, and you have a meetup coming soon, and we'll put the link in the comments of this meetup. So if someone wants to join there, it'll be cool. Okay, Misha, are you here? Can you unmute yourself? Hey.
Hi.
Great. Can you tell me a bit more what you are working on right now?
Right now, I have a couple of projects. One of them is I investigate the emergence of success in the field of science studies. That's sort of my day job. Apart from that, I'm working on this one Scala module, which is basically geared towards analyzing and extracting so-called work records. Work is some very specific format by the Internet Archive. For those of you who know what it is, it's basically a very large NGO. Well, it's not that large actually. And they try to collect and scrape information off the web and store it and archive it.
Cool. And what can you, how and why did you become involved? So what motivated you to get
in the job or in the PyData thing?
In the PyData.
In the PyData. Well, I think my first PyData was in December 2000. No, it couldn't be December. Might have been January 2018. And I basically wanted to get more involved in just data science because I wasn't quite as happy with physics as Maria is for multiple reasons. So I wanted to switch a little bit. And since usually physics allows you to get a lot of experience in programming, or at least if you're in theory, it was a fairly easy switch. And I tried to find some community that is sort of as close to my interests as possible. And PyData ended up being it.
Yeah, I did simulation, CFD also, and did the switch. But,
yeah.
And I think like finding those communities is also helping a lot to know what you need to know, basically.
Yeah, exactly. Like the talks are interesting. Plus, you get sort of your finger on the pulse of what's happening right now in the city. What's the, not necessarily the state of the art, but what is a more well, professional and non-academic stance on all of these developments. That's what I actually liked about PyData the most, that it wasn't as academic as I was used to. And I really enjoyed like all of it. Like if we had meetups at Zalando or I mean, there were so many different meetup locations and so many different hosts. It was really interesting just to hear their business model. That was also very interesting for me as well.
Yeah. Hopefully we can meet each other quite soon.
I hope so too.
Let's see.
We'll see.
Let's
keep
it
happens.
safe for the moment. And really quickly, the last one, what would you recommend to someone who wants to get involved?
If you want to get involved in PyData, just approach people and be patient. And I think the consistency is the most important part. I think if you need some consistency, or if you like consistency, or if you are consistent in your behavior, I think this is very useful, and it will help when you want to get involved in PyData. Plus, today's my birthday, so I'm probably missing the second talk. I'm sorry, Ali. But I have another meeting with.
Now take your time. It's your birthday.
It's my birthday. Yeah.
Yeah. Happy birthday.
Thank you.
Happy birthday.
Okay. Okay. Well, thank you, Misha. Happy birthday.
Thank you.
See, like that's consistency coming for the meetup for his birthday. That's great. Yeah. So thank you again, Yasmin and Misha, for the interview. So I hope you don't need to be a Python core developer to be a PyData.
No, not at all.
Olga. So if you need to be interested, want to give something back to the community, and you can basically. Hope that kind of motivates some of you to go and do that. And now we will welcome the second speaker. I will just continue and present it if it's okay for you, Adrian. So Ali is a data scientist who worked 5 years in the engineering customer experience, and it will present us what he is doing for the UK rail industry. So he's based in London, and yeah, we're really excited to see what he will talk about. Ali, can you unmute yourself? Yes.
Yeah.
And
So hello, everyone. Thank you very much for having me. Adrian, it was really good. Theo, thank you very much. I really enjoyed the talk as well, Maria, on the quantum computing. I think there is a lot of potential in that space, especially if you look like 5 to 10 years ahead in the machine learning space when it comes to big data. Just to give a background to myself before we go into the presentation, basically, I'm a senior data scientist now working for a tech startup in London called Hack Partners, and we build rail tech products and predictive or data analytics solutions for the rail clients, rail companies. And this specific talk that I felt like I could share with you today would be more related to NLP or natural language processing, and it would give you a really good high-level introduction to what NLP is all about. So if you've never done NLP before and you want to get an introduction, this talk will give you the most of the concepts, high-level concepts, as well as I will show you a demo running live code, so you can see at the same time what those concepts translate into a real-world application. And this application is currently deployed on Azure services that is basically being visualized on a client's dashboard to help them with maintenance of their assets. So without further ado, I'm just going to share my screen. Let me know if you can see the screen. All good?
Yes, we can see your screen.
All right, perfect. So my background is actually mechanical engineering. So I did a traditional degree in mechanical engineering, and I worked for a consultancy in London within the rail sector, mostly working in data and operational modeling with like Python and data science tools such as Pandas or NumPy. On the side as well, I worked on digital railway signal processing. So digitizing the railway industry, such as the signaling systems become digitized and they use lots and lots of data processing tools. For this specific talk, the context is in natural language processing. So one of the biggest problems that the UK railway industry has is that they don't have like a proper predictive or reactive data-based maintenance system for maintaining their escalators and lifts across the UK rail stations. So currently, the way it works, people just call each other up and ask about the assets, and if an asset requires maintenance, they just basically send someone to just maintain it. And instead of like using a data-driven approach, they just basically do more like a scheduled approach where they just schedule every month or every 2 months to just check up all the assets and figure out if any of them are requires maintenance or replacing components. And usually these assets have like a lifetime of 25 years, and they just do it like every month or something like that. Some assets more, some assets less. And also if there is like someone get trapped in the lifts or in like an escalator breaks down, they try to like approach the problem in a more reactive way. So they wanted to use data to use like sensor and data and maintenance reports to basically figure out how they can actually make this more predictive so that they don't spend a lot of time and money on like maintaining these assets. So the data I'm working to today is mostly maintenance reports that are populated by some of these maintainers that they go on site and like they check up the lift and escalators, and then they sit down and then write the text on their basically device that then submits it to their database. And there is a lot of maintenance report data. There is at least 250,000 reports like over the past 10 years. So what they wanted to do, one of the things that they wanted to be part of this dashboard was to have a chart that shows what are the failure types of all of these assets. So read me the maintenance reports, all of these 250,000 reports, and tell me why that asset failed. Was it like a air leakage? Was it the oil of the hydraulic ramp got broken? Was it like the door got stuck? Was it the lift got stuck? Like what was the failure? by reading the maintenance reports. And like these are, let's say, texts that are about like at least 5 to 10 sentences long each. So if you want to do it as a human, it's just not going to be possible. So that's where like NLP was really, really strong. And that's how this project came about. Like we tried to actually see if we can use current data science ecosystem, libraries such as scikit-learn, NLTK, Spacey, and so on to figure out, and pandas, to figure out if we can actually classify these maintenance reports and as their failure types, as labels as the failure types. So to give you an idea what NLP is, it stands for natural language processing. And it's an interdisciplinary field between computer science and linguistics. It basically allows computers to understand human language. There are lots and lots of applications. There is a spam detection, sentiment analysis, which is basically reads a text and figures out if it's positive or negative feeling for the person who wrote it. It's about text generation, question answering, which usually is applied in like bots or conversational interfaces, like chatbots and so on. This specific example is about classifying documents or classifying a bunch of sentences as labels, and there are multiple labels. There are at least 20 or 30 labels we want to classify these sentences by. So the first idea that comes into mind is using machine learning. So, the data set is an unlabeled data set, and we want to label it. So what is the appropriate machine learning approach here? Does anyone want to answer?
You can try to type in the chat if you want to answer. That will be easier than unmute everyone.
So I will basically ask you questions to make it more interactive, more fun. So the right approach, the right answer is that because it's unlabeled, well, the first thing we're going to try, let's try to basically cluster, use unsupervised machine learning and cluster these reports to figure out what are the biggest words or clusters that pop up and what are the themes. And based on that, we go and label them. If the clustering algorithm works, that's it. That's the problem solved. We can just basically get these reports, put it into scikit-learn, and then scikit-learn just clusters it for us. We just have to assign a label to each of those labeled numbers. As like, this is like entrapment, this is oil failure, this is like door failure, that is like the gearbox is broken, and so on, where make it easy go forward. So without further ado, let's jump into code so I could show you exactly what the data set looks like, and so it makes it more, real world. So what I'm doing here is I'm just basically importing a bunch of packages, and to give you a bit of context, I'm just going to go top to bottom and show you what these packages are. So pandas is straightforward. We use it for data analysis manipulation. NumPy as well, if we're going to do some manipulation with numerical arrays and matrices. Then we are importing here a bunch of libraries that we can use as NLTK is used for natural language processing toolkit that we use for processing text. Spacey is a more advanced NLP library. Regular expressions, again, it's to do with text, so we need that. Scikit-learn is for our clustering algorithms. So if we want to do some clustering, we're going to use scikit-learn. And pickling is just basically to save some data. I'm also importing some stuff to do with multiprocessing and functools. At some point, I will need to use parallel processing, so like put it on different CPUs so they could run in parallel. So I'm importing these tools as well, which are native to Python. Counter, so that I could count words. And there are also a bunch of other stuff that I'm importing from NLTK. So these are like stop words and some other functions that allows me to do my job doing NLP. And I will go into all of these, what these things are. From scikit-learn, I'm importing TF-IDF vectorizer and k-means. I will go into those as well, like exactly what they do. So these are just basically, I'm doing some initial setup here, basically initializing my wordlet lemmatizers and my stop words. And stop words are basically, they refer to words in the sentence that are useless. for doing any kind of machine learning. Think of or, if, and not, stuff like that. So basically, when you take a sentence like this is a sample sentence, you basically use stop words to basically filter out all of those things that is not very, very relevant. So for example, in this, you don't see off there because these are the stop words. So there is just this list of words that are not very useful. They don't add any value when you try to put your text into an array and work with it. If you have worked with Python before, all we're doing in NLP is just basically working with textual data and working with strings. So it's a lot of string manipulation under the hood. It's nothing like all of these libraries. What they're doing is just doing a lot of textual processing and manipulation under the hood. So it's not anything much important. And I'm basically doing here, just basically setting my maximum width so I can show you some of these texts in pandas. So let's import the library, and let me show you how big this library is, this data set. So it's just taking some time to import the data set. I have defined the columns I want, where the data set is. So it's lift and escalator mass default data set. And I'm just basically defining some data types for the columns that I need to work with. I'm also basically explicitly changing some of these columns that didn't actually go through properly, just to make sure it is working as I wanted. And then I'm going to sample just 10 rows of data. So there is 125,000 rows of text with 5 columns. Here's a sample of the data set. So lift is out of service, not responding, running poorly in travel, identified fault with QXT and pump. So maybe there's an issue with pump, return to site, remove oil from tank, blah, 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 blah. Out of service, already switched off. Again, not of service, doors are not opening. So this is like an issue with the doors. Stuck between floors, again, asset obstructed and stuck, lift stuck at bottom floor. And you can see it's like this. It just goes on and on forever. And it does have some labels, but these are very high level. It just basically says, is it misuse vandalism or wear and tear or aborted visit? It doesn't say anything like in detail, like what was it that was broken? Was it like an obstruction? Was it like someone got stuck indoor inside? Like what was it exactly that got broken down? So what we're trying to do is we're trying to use NLP to assign labels to these rows to show us exactly what are the distribution of like, various types of failures, so we can actually go and assign a strategy to our so that they could go and assign a strategy to their maintenance strategy. And one of the things you would also notice is that a lot of these are, so these maintainers actually have fat fingers. So when they write, there's a lot of like mistakes and there's a lot of like misspellings. So that is another headache that we need to sort out, because when it comes to working with when we're going to tokenize this data and like work with it, it's going to cause issues if we have like a bunch of misspelled words. They're going to be exactly the same words, but because they've been misspelled, the computer doesn't understand it. So it thinks it's just like separate new items that it needs to work with. And all I'm doing here is just basically I define my own EDA function. So I could look into like each row and like get various reports of like what are the sample of each column and then the distribution of them. Straight when we look at the column type, cost type, we can see that this data set is hugely unbalanced. There is lots and lots of like rows of data that is to do with wear and tear. And a couple of them, like at least 1/3 as well, is to do with misuse vandalism. And like others, like hot weather, storm damage, flood damage, and all of those other things, they are not actually as much seen in them. So our challenge is to basically divide up these 4 categories into more categories with our labeling to allow us to work with data set going forward. So what I'm going to do is I'm going to take a copy of my current data set. I'm not going to touch the original, and I'm just going to work with the copy. I'm going to get rid of all the line breaks. So I'm just basically replacing all the line breaks with spaces using regex, and then just taking a sample of data. The issue with this N is that when you import this raw data in Excel, so because this data set, they open it up in Excel reads the ends and has line breaks and it shows them nicely formatted. But when you import it in pandas, you have these like dash ends all over the place, and you cannot work with it. If you pass that in, it's just gonna not really like it as such. So we're getting rid of those and replacing them with space so we can get really clean, just bunch of texts. And the two columns we're gonna work with is these two columns that I just highlighted. Next, we're gonna do the first thing we're gonna do. So the first thing we need to do is spell checking. There are a couple of algorithms for spell checking. And depending on the algorithm you choose, your application will take either hours and days and weeks and months to spell check your document, or it could take a couple of minutes to spell check your document. That's how far these algorithms are like far apart within each other. So normally what these algorithms do is they would try, like in a native approach, they take a misspelled word and then just they look into a dictionary using an edit distance, so how far like it needs to check other words. And if for each word, and so your data set is 125,000 rows of data, each row has 5 to 6 sentences, and each sentence is about 10 to 20 words. Do you know how many words that is? And it would take at least 1 second or 1 to 10 seconds to check each word using the naive approach. So it would take you ages, even if you do it on like multi-threaded parallel processing. So that's what the native approach does. With Peter Norvik's approach, it plays around with the word. So it tries to delete some parts of it, transposes parts of it, replaces parts of the characters, and insert parts in there to figure out what, to basically magically land on a dictionary word that matches that correctly spelled word, if that makes sense. So it takes a misspelled word and then plays around with it to get to a matched word that is in the dictionary. Still, with that one, you have 2n to the 2n plus a minus 1, like in terms of complexity of the algorithm for it to run. So it's not very fast. And lastly, we have the symmetric spelling SymSpell algorithm that uses deletions and plays around with that to get to the algorithms. So instead of using transposes and replaces and inserts, it only uses deletions to figure out what is the correctly spelled word in regards to the word that we're trying to look at. So if we're just going to run this, I'm just going to show you what I mean by this algorithm working. Look at the escalator. So that's the word that is being misspelled. When I just run this algorithm SymSpell on one row of data, a couple of rows of data, the escalator is not fixed. So if we're going to bag these later on, if we're going to tokenize all of this text into bag of words, this allows us to basically get rid of all the invalid items and unclean data. So just basically that's what we're doing, is trying to clean the data here. Next, what I want to do is I want to show you some tasks to do with multi-thread parallel processing. So here we showed that we managed to clean the data for like 5 rows of data. But let's check the algorithm SymSpell and see how fast it is to run. So we want to basically calculate how long it's going to take for us to clean the whole data set. So again, remember, it's 125,000 rows. So in order to clean it properly, that's what we need to do. So if I just run it on one CPU, it's going to take me 467 milliseconds. What do you think it would take me if I parallelize it into how many? I have 16 CPU cores. So this is 50 rows of data. Feel free to post in the chat box.
300 milliseconds.
Less. So is it going to take less or more? 300 milliseconds. So let me bring up my CPU system. So these are my CPUs. They're not running as such. Let's run it now. So now all of my CPU cores are running at maximum full speed, trying to process 5 rows of data. Sorry, 50 rows of data, and spell checking 50 rows of data. And let's see how long it will take for it to process. So timeit function is a magic function that comes with Jupyter Notebooks. It allows you to basically time your code inside Jupyter. The way it works, it uses statistically, it runs your code a couple of times. So it runs it. So for this one, it figures out how many times it needs to run it. And in each run, it basically loops through the code that many times. So this is running this code 7 multiply 1 loop. So it's 7 times. And it figures it out how many times it needs to run that code in order to figure out how long it would take. So it would basically to give you an accurate estimate on how long your code will take to run. What I'm doing in this one at this bottom with specifying these parameters is I'm trying to give exactly like tell it only do a 10 loop with just one run. Otherwise, it may go crazy and then never ever finish. So while this is running, what do you notice so far that this is running? So all of my CPU cores are running at max speed. What is wrong here? So someone basically actually answered the question in the chat.
Already there is a cost to start a pool. It will be better
exactly
to create the pool once outside of the function.
Exactly. So the lesson I want to mention here is that look, 15 seconds just for 50 rows of data. So parallelizing is not always the answer. When you don't need to actually use it, there is a cost to running parallelization. And when it comes to the spell checking algorithm, if you need to parallelize something, what I would suggest to do is to always go back to the algorithm and figure out if there is a better algorithm. So I spent so much time trying to spell check this data set, only to figure out that actually the algorithm I was using, which was the Peter Norvig algorithm, so the library I was using was PySpell rather than SimSpell. It was taking ages. I took it on a parallelized processing unit, and I just went for lunch. I came back, and it was still running on 16 cores, and it wasn't doing anything. Just because this symmetric delete spelling algorithm is actually 1,000 times faster. So you can see this code ran for 7 runs, and it took 15 seconds. This one ran for 7 runs, and it took only 400 milliseconds. So it's like orders of magnitude faster. So it's not always the best thing to parallelize it. What I wanted to show in this one, so I have the output open, so I don't need to run it this time. I could just show you the output of the second run. If I scroll down, you can see that actually for 2,000 rows of data, parallelizing actually did reduce the time it would take to spell check this data set. So spell check at least 2,000 rows of data. So as soon as you become bigger and bigger, go into bigger data frames and bigger data sets, it does make sense to do parallelize. But again, I would always say go back to your algorithms and to your code base and try to think if the parallelizing is actually the right thing to do. So that's just basically what I wanted to mention here. Next thing I'm going to do is one of the things I was most interested in was what are the most common words in this data set. So if I want to do some clustering, what are the kind of labels that I will need to play around with, and I will need to suggest when it comes to building the machine learning or clustering model. So all I'm doing here is just looping over my data set, tokenizing it. And when I say tokenizing, I mean just basically taking a sentence, taking a text and then dividing it into sentence, or taking a sentence and dividing it into basically a bunch of words. So this is called tokenization. So tokenizing it and then basically lemmatizing it and checking if it's actually a word rather than a number, and if it's not in the stop words. So only include words that are actually words, they are not stop words, and they are actually the base word rather than like variations of the word. So for example, variations could be clothes, clove, clothing. So all of these, the base word is clove. Yeah. So that's what lemmatization does. So when I talk about lemmatization, in stemming, we just basically take the base of the word. In lemmatization, basically you're taking all sorts of variations of the word and then you're just basically replacing with one word. So when it comes to counting number of words that have been done in your data set, so when it comes to an operation called bagging, which takes a piece of text and then puts it into a counter object and counts how many times that word has been, been appeared in the data set, it doesn't it's very clean and it's very, there are no duplicates in that. So that's why I'm lemmatizing at the same time. And that's what's happening here. So I wanted to identify the most common words in the corpus, which is here. There are 173,000 mentions of lift. So this data set is mostly talking about lifts that are out of service on the platforms. And then there are some escalators and then doors. So you can start to see like what are the most common things that are happening in this data set. So when it comes to building your machine learning model, what are the kind of words that you will need to worry about when you're doing that? Again, so when I built this, it doesn't provide me with much context. It's just basically a bunch of random words, other than like entrapment, which could be a good useful label to use, alarms, and so on. So I continued with doing something that is basically building my unsupervised machine learning model. So I think if I'm right, Adrian, you're working on scikit-learn, right? As the maintainer. I think this part you would like this. So I'm basically importing something called a TF-IDF vectorizer from scikit-learn text features module. And what I'm trying to do here is I'm trying to use the k-means algorithm with a maximum iteration of 100 and initializer of 1. With how many clusters? I am doing 5 clusters, 8 clusters, and 15 clusters to train 3 models with different number of clusters to figure out what are the top 5 categories of data, categories or labels that this models is trying to figure out. So I'm initializing my TF-IDF vectorizer, and I'm going to talk to you exactly what this TF-IDF vectorizer is doing. So what these are building the models. So let me run all of them. So it's building 3 models now. What it's doing, building those 3 models and training them. Let's go back in here and talk about what TF-IDF is actually doing. So TF-IDF, actually what it does is called term frequency over in the inverse document frequency. So what it means is that it counts how many times a word is appearing in a document, but it doesn't appear in other documents. So for example, if you have a document about Albert Einstein, words like gravitational theory and relativity will appear the most in that document, but it doesn't appear in a document that is about Tesla and Nikola Tesla. So that document is heavily balanced towards those words and it's about those words. This is similar to what like Google does when it comes to do SEOs. So like when it comes to your website and your website is about some specific keyword, the TF-IDF score of your website is on that keyword. And it's just a nice feature engineering approach for understanding how each report is related to what label. So that's why I'm using TF-IDF vectorizer, which is basically it's vectorizing at the same time and calculating the TF-IDF score, which is the axis bottom, in order to build some features that it could use in order to build the clustering models. So in order to figure out which words correlate with each other and put them into clusters. So if we look at the first cluster, so the 5 cluster model is built and we have used it to, we are basically now printing some of these clusters. We can see that the first cluster is about lift, platform, service, entrapment. Second cluster is about stuck, level, lift. So maybe the second cluster is about talking about being stuck in a lift. The first cluster is about, again, being entrapped. The second is about getting stuck. The first one is about people getting entrapped. The third is about escalators tripping or accidentally restarting. Basically, I'm not getting enough information from this. So I clustered my data set. It's not giving me enough information to basically go and build, go and label these rows. So apparently, even if I use different clusters, different number of clusters here, I don't think there is enough data in each report in order to train a good model that would allow me to label these rows. So even if I go and predict on these rows, and I see like some of these have been labeled 0, 1, and 2, the ones is about passengers getting, or the lifts getting stuck. 0 is about smell of burning rubber, lift not working, and chairlift on booking office site stuck. So actually, this is not doing a really good job because these labels have nothing to do with the rows. There are like some bits that are not exactly there. Again, same as this one and same as this one. So what I try to do here is I try to use unsupervised machine learning, and it didn't work. It's just not performing the way I wanted to, just because my data in each row is not enough for me to build a machine learning model on top of this. What do you think would be the best way now going forward? So I'd have an unlabeled data set. In order to build any model on top, I need to label it first. What would be the best way to go forward?
We get from Les guessing a frequency distribution of n-grams.
That could work. What else can we do? So I didn't do the n-gram approach. I did more like a hardcore approach, I would say. So I thought, okay, I have an unsupervised machine learning problem. What if I try to make it semi-supervised? So what if I try to label some of these rows of data myself, up to 20 or 30 labels? And then if I can label most of the data set, then maybe I could train a model on those data sets in order for the model to then label the rest of the data set. Does that make sense? So it's called the semi-supervised machine learning. So that's what I started doing. So first I thought to myself, okay, first the spell checking didn't work properly. It's just gonna take ages for me to do. What if I try to, instead of spell checking the whole data set first, I'm gonna bag the data set. So I'm gonna use bagging to bag my data set. So if I look at the bagged words, you're gonna see basically a bunch of counter objects as well that would just show you how many times each word is appearing in each sentence. Then instead of going and basically spell checking all of the texts in each row, I just basically spell check the bags. And if there is any duplicate bag that I've spell checked, I wouldn't do it. I wouldn't spell check it anymore. So it just basically reduces the overload, so the computational overload on the computer. So it only spell checks unique bags instead of like going and spell checking the whole data set. So that's one of the things I tried to do to actually reduce the amount of computational power. And this is actually now is bagging some of these words. So I'm just gonna run some of these functions. So all these functions are doing is just basically spell checking the bags instead of spell checking the actual data set itself. So all of it, concatenating all the text together and then spell checking that text. And when I do time it, then it would allow me to show you how each a different algorithm is working compared to each other. So now the bagging is done. So look at the bow juice and bow lock columns on the right-hand side. You would be able to see what bagging does. So what bagging does is that it sees this. There is two words called Stana. So Stana is the name of the lift company. Is being appeared twice in this piece of text. So now with bagging, I have some kind of feature that I could use to label these. They label these rows in a different way compared to just using this unsupervised machine learning model. However, I still do have some issues with spell checking. Some of the words have basically incorrect spells. So what I need to do is I will need to spell check all of the keys and then basically combine their values. So combine the counts. If those two keys, when I spell check them and it's corrected the key and two keys are exactly the same, it needs to basically add up the count of those two keys and basically to get rid of one. So that's what I'm doing with these functions down here. It's just I'm basically spell checking and then basically combining them back up. just to show you how much difference there is into the algorithms, so like using the algorithm, I'm just going to basically spell check one row of data using Norwich algorithm, and then I'm going to spell check one row of data using the sim spell. So the Norwich algorithm took 2 seconds using one loop, doing 7 runs. It took 2 seconds to run the algorithm, but with the symmetric spell algorithm, it took 1.6 milliseconds. It ran for 7,000 loops. It basically ran it 7,000 times. It only took 1.6 milliseconds in each time. So this is orders of magnitude difference in the spell checking algorithm that I've used. Just because I basically used the correct algorithm instead of like going and using a very more naive approach. So if every time your application is like not doing it properly, make sure that the algorithms that are using out of the box actually are performing really well compared to other algorithms that are out there. So what do you see here, what I've done here? So I have basically went into the data set and then just some hardcore EDA to figure out what are the different types of issues that have happened within this text. So I said to myself, okay, I'm going to convert my unsupervised model on my unsupervised data set into a labeled data set. But instead of like try to build and like figure out using a frequency distribution of n-grams or anything like that, I basically just sat down and wrote this massive dictionary, and I used a min match. So min match key to categorize these labels. If there is too much of these words, then it's definitely door failure. So if there is a word that says door and then it's not open or something like that, there is high chance it's door failure. And then I basically use this dictionary to label my data set. It's a very, very simple hardcore approach. So I don't recommend it unless like you're on a tight deadline, or in some cases, it's more relevant compared to using machine learning. It's just basically more easier to do. So I'm just going to show you basically what it does. So what I'm going to do is I'm going to run this scripter on the data set in order to understand how the rows of data is actually now being categorized. So if there are words in the bags that are to do with alignment, align or aligned, it's to do with misalignment. If there are words in the bags to do with overheating, heating or overheated, that's to do with overheating. Power failure, again, to do with power failure, and so on. So I didn't use a lot of different labels, just basically these, so that I could get like some idea on how I can label my data set. And if I can get this to work, then I kind of have solved the problem, even if without using machine learning. So let's look at the data here.
Will that be possible to finish in around 5 minutes so that we get time for some questions?
Yeah, it is near the end.
Perfect, great.
Yeah. So then I ran this, and basically what I got is this one. So you have the label column on the right-hand side, and then you have the text column on the left-hand side, and I'm sampling 10 rows of data. So immediately when you see is that there is actually like the labeling seems to be working. If there is something to do with noises, so lift doors are making strange noises. So there is an issue with excessive noise. Flooding, platform 5 to 8, subway water in pit, sign flashing requires pump out. So maybe there's an issue with flooding. So it does seem to be working to some extent. So we do need to do some kind of analysis on this to figure out exactly if it's done a good job at labeling the data set. But now, if we look at some statistics in regards to how good the labeling has done, there are only 8,000 rows of data that is not labeled now. And these rows of data, when we look at them, the text itself doesn't say much about that row. It says, please ignore first set of times, engineer on site, blah, blah, blah. So there isn't much information in this text anyway, in order to help us understand what this report relates to, like what is the issue with this lift or with this escalator, even though when we have backed it and we did with everything else. So apparently, even though I did hard code my dictionary, to categorize my rows of data, it did work by me just basically using bag of words and doing all sorts of like standard data cleaning features to do with text. So if I just look at the data, this is what it looks like. So first thing I noticed when I ran my data set is that actually I think my dictionary is not very well, because I do have a massive unbalanced labeled data set to do with asset, obstructed, tripped, and jammed. And the rest are like not as many instances of that in the data set. So what I thought to myself, actually, instead of having this labeled dictionary on top, I could break it down into more labels, and I could follow the same process and break down the labels even more in order to make my labeling more refined and more detailed. So if I go ahead and do the same thing, and I show you how the labeled data set would look like, it would allow us to get an understanding of basically how performant our scripted classifier is. And it would also allow us to go ahead in the future to build using Spacey, which is an advanced natural language processing library that allows you to build neural networks and to program neural networks, to train a model now on this data set to figure out, to build a model that would later on look at more reports in the future and basically categorize them in the right categories, depending on what the failure type of that asset is. So here now you see that after I refined my dictionary, I'm actually getting a much better, more balanced. It's still unbalanced, but it's more to do with the data itself than to do with the way I have defined my categorization dictionary. So it's doing much better, and I have like a good balance of like flooding, misuse, excessive noise, light failures, and so on. And there's like 2,500 instances at least of these ones. So it would allow me to, it gives me enough labeled data set to convert my unsupervised machine learning model, the machine learning problem, to a supervised machine learning problem, or semi-supervised machine learning problem. So when I tried the model, I could then go back and try to label all of those rows of data that have not been labeled before. So that is basically what I tried to do going forward. However, because the application was meeting the requirements to some extent, this work has not been done, but this could be something that could be taken forward when it comes to, for example, classifying various types of failures when it comes to entrapments. Why are there some of the reasons that people get entrapped in lifts? And if those type of labels are inside the text to do with entrapments, then you can maybe use and train a model on top of that in order to go and do this. So with that said, this concludes the talk and concludes the demo. I'm happy to answer any questions you guys have going forward on to do with this.
Clap. Okay. We just get a question from Evan. Is the data set unbalanced because of the types of machine breakdown? Because the types of machine breakdowns is unbalanced?
So the lifts and escalators mostly get obstructed and have door failures just because some components fail more than the others. So there is a higher chance that the door of a lift fails because a lot of people use the doors. So the doors keep opening and closing. So statistically speaking, if a door keeps opening and closing, there's a higher chance that the door would break compared to the gearbox or the power. So the data set is unbalanced because it's a real world data set. So because of the because in a real world, the failures are unbalanced.
Yes, makes sense. I got another question from Let's Guessing. Did you consider using topic modeling?
So that could have been something that I could try, yes. So there are different approaches that you can take. One was, someone mentioned frequency of distribution of n-grams. The other one could have been to do topic model and figure out like the relationships between different topics and these labels. So that those are areas that could be investigated further, yes. But I at that immediate time, because this was under the deadline, we were trying to just produce something that we could put on the cloud to categorize these failures. We basically stick with just this simple solution of a dictionary that uses the second min match key to identify what category it needs to categorize for each row.
And what are your thoughts about using name entity recognition for labeling purposes from Evan?
Again, the same thing. So named entity recognition for labeling depends on the text. So it's usually more useful when you have like text that would say it has people in it, it has like dates and things like that, like when it comes to performing named entity recognition. I don't think in this data set, or at least in the text, because the text is so specialized, it wouldn't give the named entity recognizers enough to work with in terms of features that would allow you to build something like a good machine learning model on top. So normally those recognize people or dates or like locations or things like that. This data set was talking about like objects or assets or things like that in the data.
Makes sense. Yeah, already answered. Cool, thank you. Any other questions? I have one. So this have been deployed and it's currently used in the UK, right? Do you have any future plans, or is it the project on?
I'm sorry, I couldn't hear it. What's the question?
Is it deployed?
This is deployed, yeah.
And will that, are there any plans to improve it? Are you still working on it and improving it, or is it?
Yeah, so the plan is to develop this further when it comes to the second phase of the project. So one of the things this doesn't provide is that so whenever you see like the number of entrapments we have in lifts, there are at least about 5,500 or 6,000 entrapments. We don't know why these entrapments are the case, and we want to know that further. So when it comes to building a more accurate model or a more accurate way of doing this, we will need to build a more accurate solution, and then that accurate solution will then be reapplied to this as well, so that you get more accurate labels, and you also get less I would say unbalances in the data set if those unbalances is issued by your approach.
And also quite related with the question, maybe you can add. So what have been the feedback since you deployed? So
this has been recently deployed. So we're still basically waiting for the data to come in and see how the data is being automatically labeled when it comes to the labeling.
When has it been deployed?
It's been deployed, I think, 2 months ago.
Okay. Yeah. Okay. Any other questions? We still will get quite good comment from Let's Guessing. Great to see a real-world application of NLP. Very cool. I completely agree with you. Let's Guessing.
Yeah.
That's really cool to see. Basically, real data science working.
Yeah.
You really see how it's working in real life.
Yeah.
I get a question from Christian. Do you see as an option to have separate models per label or label set, and then accept some results with some threshold, like acceptance rate?
So that is a good idea. So you could actually train for each label, you could basically train separate models that would be very specialized on that label. And what that would entail is that, like, for labels that have a lot of data, such as asset obstructed and door failures, that models will then become really sensitive to if exactly it is a door failure, it would label it as door failure. So these are actually ways you could go and improve this approach, which is like a very simple, just dictionary-based approach, into a more robust model-based approach, where you have like it considers all sorts of noise in the data and figures out that actually it's just not seeing the words in this text, but actually there are some relationships between these words that make that report related to door failure. So that is a good option, and that is something that could be worked on going forward. Another thing I want to mention is that this data set is unbalanced from light failure onwards. So light failure to air leakage, there is not much data to work with. What you could do is you could do something called synthetic minority oversampling technique, or SMOTI. And what SMOTI does is that it generates synthetic data by interpolating between data points. So you generate text by interpolating, by learning some of the patterns of the current samples that are undersampled, and basically trying to increase the training data set in such extent that the labels are balanced now. Even though data set is unbalanced by nature, the data set will become balanced just by you doing some kind of synthetic minority oversampling technique on top. So that is something that could be looked into to see how we can actually reduce the imbalances, so that the models we train have more training data. And if we want to go with one model, that one model becomes more generalized compared to using 16 models or 25 models, or how many models there are. The problem with models is that you will need to deploy them, and then you will need to send requests to them. And having one model will give you less cost on the cloud infrastructure compared to having 16 models. So it's not just about building the most accurate application, it's also about costs. So if you can build a generalized model that can perform well on all labels, it's way better compared to having 16 super specialized models.
Speaking of the imbalanced data, do you happen to also have checked the imbalanced learn?
Checking
it's
the
another library maintained by some of the scikit-learn maintainers. It's called imbalanced learn.
Imbalancer.
Imbalanced learn, as in like
imbalanced learn.
learn.
No, I haven't seen that one.
Yeah.
No, that is interesting.
They have some good tools.
So it does oversampling and undersampling and ensample. Oh, this is good as well. So there are like lots of different ways. So it does have SMOTI.
Yeah.
Cool.
So this is kind of it would look like. So the yellows, you can see loads and loads of the yellow dots. And the purple dots are not a lot. And basically it's doing some kind of interpolation to increase the green and yellow dots to some extent. And then there are some purple in there, but it's increasing the purples a lot. And by basically interpolating between dimensions of data.
Okay. Any other questions? I think we are. I think we are good. So Adi, thank you very much.
Yeah,
again,
thank you very much.
Clap, 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 clap. So you will be able to share the slide if people are interested. But the code for some reason, for some company reason, you will not be able to share. So we understand. But thank you very much to share everything with us.
Yeah, well, I will try to see if I can share the code as well. So I will ask, and then if it's possible, I'll try to share the code too.
Yeah, great. Okay.
Cool. Also, thanks everybody for joining the meetup, either on Zoom or on YouTube. We will be now. I'm gonna stop broadcasting on YouTube, but we may continue hanging out on Zoom.
I just as a reminder, so there is a next week a meetup in Jeddah with Yasmin. So if you're interested, check it out. We'll put the link. And yeah, the PyData General Conference in November, and they call proposal until the 2nd of August. So if you are interested, just check it out. It's